So this set of video clips, we're going to be looking at force as a vector quantity. I'm going to be using three identical Newton balances, and I just want to draw your attention to a mark that I've put on the scale here. Okay, so the brown mark, if you see on any of the three Newton balances, that brown mark is on the 5 Newton. So at the moment I'm actually using a force, a pulling force here of just over 8 Newtons to allow you to actually see this. Okay, it's about 8.3 Newtons I'm using. Okay, so if you see a brown mark on any of the Newton balances, okay, you're looking at 5 Newtons. So this next wee clip, I've actually got two Newton balances pulling on each other. Okay, the left hand one you can see here is actually held by a clamp stand. The right hand one, okay, across here is actually held around the leg of a chair. Now I'd like to draw your attention, okay, to the two brown marks that you can see here. Alright, so remember those brown marks are on the 5 Newton point on the scale. So these Newton balances are actually showing that there's an equal pull on them, okay, 5 Newtons either side. This is a good example of both Newton's first law and Newton's third law. Newton's first law, if you remember, states that if forces are balanced, an object will remain at rest. Well, these Newton balances are not moving, right, or alternatively they would move a constant speed in a straight line. Newton's third law states that if A acts on B, B acts back on A. Okay, remember that's action and reaction. So if we say that this one here is pulling on this one, then this one is also pulling on that one. Okay, and you can see the forces are equal and opposite. So the resultant of this is actually 0 Newtons. 5 Newtons in one direction is being cancelled out by 5 Newtons in another direction. So overall force acting on this is 0. I am now going to apply another force, another pull, okay, using the Newton balance that you can see on the right hand side of your screen here. I'm going to have to try and work really hard at keeping this one here at 5 Newtons. Right? I want to keep the brown mark right on the end of the scale here. Right, so I'm going to have to work quite hard, but what I'd like you to pay attention to is what happens to the brown mark on this one. This is going to be my, what they call resultant force. So if I start to pull on this one, you can see the brown mark moves, okay, as the scale moves. So actually the force here, okay, is actually increasing. This is having to work harder now, right? And it's because I'm now having to add these two forces together, okay, as vectors. Now there's a rule when we're adding vectors together in that we must try and keep the geometry correct, the angles between them. This level we'll only be looking at vector quantities acting at right angles to each other. And I happen to have drawn two vector quantities here, and just in terms of these arrows, okay, at right angles. So if these were two forces, I think it'd be safe to assume that the object would go somewhere along that direction there. To actually do this correctly, we need to add these vectors nose to tail. Now what do I mean by that? Well, at the moment, these two arrows are touching tail to tail, right? This should be the nose of the arrow, this should be the tail of the arrow. So I've either got to move this one up, again, keeping the geometry the same, so I'll still have a right angle up here, or I move this one along. Again, I would still end up with a right angle here. The crucial thing is, no matter what would happen, when I complete the triangle, I'm going to end up with a resultant somewhere along the line of that pen. So, if I was to move this one along the way, okay, so that the tail of this vector meets up with the nose of that vector, which is my kind of yellow or orange pen, I would end up there, still got my right angle. If I choose to move this horizontal force, you might be looking at it here up the way, again, nose to tail, I'd end up where the red arrow is. And again, I would be keeping the geometry the same. I've still got a right angle in there. The resultant, okay, the overall of those two forces then would be along the line of where my brown pen was. Okay, it's going to be there because that is now adding nose to tail. No matter which way I go, I end up with the same resultant. And I'm going to draw that as a dashed line. Now, you'll have probably come across trigonometry and Pythagoras' theorem down in maths, and this is how we actually calculate the length or the value of that resultant force. This is obviously the hypotenuse. No matter which way I look in terms of these right angles, when I've added up the two vectors correctly, this dashed line, okay, is the hypotenuse. So the other two lines, okay, would be my adjacent and my opposite values. So if we use Pythagoras' theorem, where we say that R is the resultant, the diagonal, that dashed line that we saw in the diagram, R squared would equal F squared plus F squared, because I said the two forces were actually the same value, the same size. And therefore, if we try to find R, we've then got to take the square root of that on the right hand side. So what does this look like in practice? Well, I have my 3 Newton balances again, and I'm trying desperately hard to make sure that these two are on 5 newtons. You can see the brown mark there, just at the end of the scale. And I'm also trying to keep it very, very hard that they are actually at a right angle. So if we were to go back and do our calculation of 5 squared plus 5 squared, and then take the square root, we should get this value here. So if we look at where the scale is, it's about 7.1. So the resultant of these two 5 Newton forces acting at right angles to each other should be effectively 7.1 newtons. So if I think back to the bit of practical we just saw, it was going to be 5 squared plus 5 squared in there. So that's going to be the square root of 25 plus 25, which is going to be the square root of 50. And if we do that, that actually comes out as 7.1. What did we get on the scale? 7.1. So we can actually see this does actually work in practice. Now, if we want to really put this as a vector, not only do we need the value, the 7.1 newtons, we also need to give it a direction, because a vector quantity, remember, has magnitude or size, has value, but it also has a direction. Now, normally the simplest way to describe this is using what they call 3-figure bearings. You may have done this in maths, you may even have done something similar in geography, where north is deemed to be 0, 0, 0, east would then be 0, 9, 0, south would be 1, 8, 0, and west would be 2, 7, 0. And any value in between then, okay, would be coming from 0, 0, 0, down to 0, 9, 0, and then we could have 0, 4, 3, 0, 6, 1, that would tell me the angle is relative to north. So if we look at the one we have here, this really is the angle I want to be looking at, because this is north. So I want to be measuring this angle here. And if we call this angle X, well, the opposite side for X is 5 from our example. The adjacent side is 5. And opposite and adjacent gives us the tan function, tangent. So the value for X is actually going to be the inverse tan then of 5 divided by 5, because it's opposite over adjacent would give me tan of X. Well, I want to get X, so we do the inverse of that, and that would actually give us that X is 45 degrees. Now, coming from north then, this would actually be a bearing of 0, 5 degrees. And that's the simplest way to describe them. Don't get caught up with norths and easts and everything else. Use 3-figure bearings if you're asked to try and find the direction of a vector. So let's take a word example. I've just got an object here that I'm representing by the square or the rectangle, and I've got a 50 kilonewton force, 50,000 newton force acting in that direction, and I've got a 100 kilonewton force, 100,000 newtons acting in this direction. So again, just by looking at it, we would expect this object to move somewhere in this sort of direction there. Now remember, we have to get the resultant force by adding the other two vectors nose to tail. So I've chosen to move the 100 kilonewton force up. Okay, so it's now meeting nose to tail here, 50 kilonewton still pointing vertically, which is pointing north, according to the example I gave, and this 100 kilonewton force is pointing horizontally east. So we want to try and find a value now for R. And if you remember, that's done through using a bit of Pythagoras. So we would substitute the values in. I am not changing the kilonewtons to newtons because my answer will then come out in kilonewtons. I don't have to go to all that bother. So if we then do the addition and the squaring correctly, we should get the square root of 12500. And if we do that, and I'm going to round it off, okay, because it is what I call a calculator answer, there's loads of decimal places, right, we get 112 kilonewtons. Now, because this is a vector quantity, we still have to find a direction in the force actually acts. Okay, we can see the force is acting along that brown dashed line in our wee triangle, but we need to actually express that as a value. Now, remembering that the red arrow, the 50 kilonewton force, is actually pointing north, and that's 0, 0, 0. What we want to try and then measure is this angle in here. Now, I've called this angle X. So if we were to look at this in terms of the right angle, in terms of X, this would be my opposite side, this would be my adjacent side, and for the right angle triangle, R is always the hypotenuse in this case. Okay, so my 100 kilonewtons is opposite, my 50 kilonewtons is my adjacent. So from opposite and adjacent, I would actually be able to use the tangent, right, the tan function. So if we say the X is tan to the minus 1 of 100 divided by 50, well, 100 divided by 50 is 2. So if we were to do tan to the minus 1 of 2, we would get a value for X of 63 degrees. Simplest way to express them, as I say, is in 3-figure bearings, so that would then be expressed as 063. So that's 63 degrees round from north.